finish that work problem.
Okay. The aquarium problem?
Yeah.
Okay. And perhaps
also,
go ahead.
I have a couple of things that I just need to quickly go over and clarify. I'm still not fully understanding, I don't think, when to use integration by parts versus substitution.
Okay.
I understand that usually substitution will be a simpler problem, whereas integration by parts is more of a polynomial.
First of all, understand that there are many, many techniques for integration. These are just two of them.
Yeah.
Substitution, parts, partial fractions, trig substitution. It's unbelievable how difficult it is to integrate compared to differentiate. I can differentiate any function you give me by using those four rules, the product, quotient, chain rule, and power rule. Not the same with integration. Finding the antiderivative of something is extremely tricky. And in fact, there are some functions, this particular function right here, that there is no antiderivative to that. If I try to integrate that, you cannot find a function whose derivative is equal to this. So there's all kinds of difficulties when it comes to integration. Now, as far as when we use substitution and when we use parts. Parts is almost always used when you have the product of two things. In other words, if I'm trying to integrate x times e to the x, that's the product of x times two different functions. So it'd be nice if we have a product rule for integration, but we kind of do. The way the formula for integration by parts was derived was from the product rule for differentiation. So when you see the product of two different types of functions, think integration by parts, whereas if you see a composite function, what is a composite function? A composite function would be square root of x squared plus 1. What is that a composite function of? Well, f of x would be x squared plus 1, and g of x would be square root of x. So this represents g of f of x. Okay, now where you have a, it's asking me to shut off my webcam. Let me do that.
Okay.
I wish I knew how to solve this. I don't know. I'm not positive. There's got to be something running in the background, but it always waits about 5 minutes before it tells me that.
Yeah.
But anyway, so if I'm integrating a composite function, I want to think substitution. If I'm integrating the product of two functions, I want to think parts. And parts won't always get it done either. I mean, I'm not sure what percentage of functions that substitution and parts will solve, but I suspect maybe only 10%. It's kind of like dark energy and dark matter. There's a whole realm of functions that substitution nor parts would help.
Okay.
Okay. Let's just get back to the aquarium problem for a second because I had some better thoughts on it.
Okay.
First of all, you want to set up an axis to place your aquarium at. And the middle of the axis, I would make the halfway line on the aquarium. because it's all this water here that you have to pump out, right? If I remember right, that we had to pump out a 1/2 meter of water. And I think this dimension was 2. I can make this 3-dimensional if it helps. And this dimension was 1. The best way to look at this is to think of this aquarium as a deck of cards. Okay? And instead of taking the top card and lifting it up and moving it over, imagine that that card is made of water. And the entire upper half of this aquarium is going to be these very thin slabs of water that you have to move to the top of the aquarium in order to get it out, to pump it out. Okay, well, since we're set up on the y-axis, let's integrate as a function of y. And how far, if I took this first card, the 26th card in the deck, and I had to move it out, the distance that it has to travel is 1/2 minus y. And if I took the 51st card in the deck, how far do I have to move it? Well, a very small amount, because y is very close to 1/2. So that's why the distance that we have to move it is set up as 1/2 minus y. And when I first went through this, I used x. It doesn't really matter whether you use y or x here. I mean, I'm going to use a dy as the function, or as the variable of integration. And I'm going to integrate from 0 to 1/2, because the first card has to go the full distance of 1/2, but the next card has to go a slightly lesser distance. So work being force times distance, sometimes the force is variable, sometimes the distance is the variable. In this particular problem, each slab of water weighs exactly the same amount. So the variable is the distance. And the distance that each slab of water has to move is 1/2 minus y. Okay? So we're going to set up this work function as an integral of force times distance, but it's the distance that's variable, and I'm going to use a dy, and that distance is 1/2 y. So that'll be the function I want to integrate. And the force is just a constant force, whatever the weight of one slab is, that's the force. And let's see, if I remember right, the weight of one slab is 2 times 1 times 1,000. So 2,000 delta y would be, well, actually, yeah, because since the directions are in the same, the thickness of each slab is dy, which goes along with the fact that we're integrating along the y-axis, which is a function of y. So all of this works nicely. Now, there are some kind of interesting things here. If you were to place a water pump right here and start pumping, then it's actually a different work that's being done.
Right.
Notice that if you move this slab of water out first, all the others fall down on top of it. In other words, every slab of water would have to be pumped 1/2 meter. Whereas if you take off the top slab first, it doesn't have to go a half meter, and then the slab underneath it has to go a little bit more than 0 to get out. So it presents a different amount of work.
So would that be a difference in the
Answer? Very much so. You would
no, in the limits, I mean. Is that how that would be expressed?
It wouldn't really be a calculus problem then. It would be you don't have a variable anything if you were to perceive the problem that way. In other words, if this were my deck of cards, let's say, and I pulled the 27th card out from the middle and lifted it to the top and discarded it, but all the other cards fell down so that the 28th card I pull up has to travel the equal half-meter distance, then the total amount of work is going to be constant. It's just 26 cards times the weight of each card times the distance that each one moves. So it's not a calculus problem. We only need calculus if we have a variable distance or a variable force. Now, when we did the water and bucket and rope problem, we primarily had variable forces, not variable distances. We had to lift all of them 20 feet, but the rope, the force of the rope changed as we lifted it up, as did the force of the water in the bucket because it was leaking. So these are two classic problems illustrating two different techniques for finding work. One where you have a variable force, the other you have a variable distance. In this case here we have a variable distance because each slab of water doesn't have to travel the entire half meter, at least not if you pump from the top.
Okay. Can you explain to me why it's the integral from 0 to 1/2?
Yeah, because we're going from here, we're going to take that slab of water, that rectangular slab of water, and then we're integrating throughout this interval right there.
Because we're moving it over the top of the...
Well, we're removing this slab, and then the slab above it, and then the slab above it, and the slab above it. So we're integrating throughout that entire interval. And each one that we integrate has a different distance that it has to go. The limits of integration, it's very similar to when we have solids of revolution. If I take this curve, rotate it about the x-axis so that it creates this solid, and slice it up into disks that are parallel to the y-axis and horizontal to the x-axis, I integrate from 0 to this point right there, A. Because that covers my full area of these disks. Same thing with work. I'm moving each slab of water between 0 and 1/2. So I integrate from 0 to 1/2. I'm basically summing up. In other words, that's what the integral is it's a sigma. It's a summing. And in that case, I'm going to go from 0 to 1/2 of all of these slabs of water.
So how come it wouldn't be... Okay, yeah, I guess I understand. I think that the fact that it's on the
y-axis
is messing me up. I'm
okay. It
But
kind
I
of
think I understand.
it messed me up a little bit the first time I did this, and that's why I used the x variable. Because in my mind, it didn't matter. It didn't matter
Yeah.
which axis we integrated on. I just knew we had to go from 0 to 1/2.
Yeah.
In fact, if I set up my coordinate axis here so that the x-axis doesn't lie in the middle of the aquarium, but at the top, then I would end up integrating from minus 1/2 to 0,
Mm-hmm.
which wouldn't make any difference. You still go over that same interval. But also I could rotate everything by 90 degrees here, even though the water would flow out. But if I had a deck of cards, I could certainly rotate it by 90 degrees and integrate on the right side along the x-axis. Same thing with a deck of cards, though. If I were to pick up the top half of the deck of cards and lift it to the edge of the top, that's not the same amount of work that's being done if I take the top card off and then the next card off and then the next card off.
Mm-hmm.
It's more work being done. Because in the one scenario where I take a half a deck and I move it up 1/2 meter, all the cards have moved 1/2 meter. So the amount of work done would be the weight of that half deck of cards times a half. Very simple. You know, if you have a constant force that you're moving a constant distance, if I take a 100-pound weight and I lift it up 5 feet, I've done 500 foot-pounds of work.
Mm-hmm.
Are you taking a physics class now, or have you taken
No,
physics yet?
next quarter.
Next quarter? Okay. Well, all this math will come in a lot more useful to you when you get to your physics class.
Yeah.
But you can't even talk about the math part of it without invoking physics.
Mm-hmm.
Okay. What else would you like to cover, or like me to find some problems concerning? Do some
Let's see.
problems, or you
Just a
can
couple of other quick things.
Okay.
In the book,
Mm-hmm.
well, I guess actually on the study sheet that my teacher gave me,
Uh-huh.
he mentioned something about properties of integrals, or using properties of integrals to prove facts about average values. And I'm not sure what he means by that.
Well, there's a formula for average value.
Right.
We want the average value of that function from A to B. Wouldn't be that easy to figure out from just looking at it. But it turns out being 1 over b minus a times the integral from a to b of that function.
Mm-hmm.
Now, this is fairly straightforward. What's the average value of a function over an interval? Gets a little tricky when they say, what is the value that we have to figure out a value of between A and B, some C, that equals that value. That takes the level of difficulty a notch up.
Okay.
Best way for me to help you with these is to work through problems. Now, just if you're still having difficulty with where to use substitution and where to use parts, I can give you a couple of problems and ask you which to use on which.
Okay.
And maybe how to do them. Let me go to my book since I'm not that great at making up problems in my head.
What is the integration by parts reduction formula?
The reduction formula is where you take sine squared of x and you reduce it to one I think it's 1 minus cosine of 2 theta over 2, and cosine squared of x is equal to 1 plus cosine of 2 theta over 2. Now, this is extremely useful if we're trying to integrate that or this, because we don't have a way of directly doing it. So we would use one of these two reduction formulas because we can integrate this just fine. And by multiple reductions, we can get everything down to cosine of some theta. This integrates easily. This does not. So I think that's what you were referring to. Is that the reduction formula as far as trig goes?
Could you instead of saying sine squared of x, could you just say sine of x times sine of x and just do it that way?
No, because notice
We don't have those rules to figure that out.
We don't have a way of integrating product.
Right. Okay.
So, and it doesn't integrate by the power rule. Notice that if I tried to just say, okay, that's sine cubed of theta over 3, but if you take the derivative of that, you don't get sine squared of theta, because you have to use the chain rule when you take the derivative of this. It indeed is equal to 3 sine squared of theta divided by 3, but then you have to take the derivative of the inside, which is cosine of theta.
Yeah.
So if I take the derivative of this, I get this. So it's not that easy to find the integral of that without using that reduction formula. And incidentally, that reduction formula, I may have gotten them switched. I never can remember which one is 1 minus cosine of 2 theta and which one is 1 plus. So make sure you look that up before you take my word for it there. However, let me just throw out some problems here, and you tell me whether we're going to solve these by substitution or parts.
Parts.
Actually, this is by substitution. And this is in the section that is called recognizing the f of g of x g prime of x pattern. This is the classic case where we're going to need substitution. And I'll go through how we do this by substitution in a second. But
I see, because when we do it, when we integrate, or when we
differentiate the inside of this,
we get the 2x.
we get 2x, and it ends up always being in the denominator. In other words, if let's go through it here. U is equal to x squared plus 1. Now we go ahead and find out what du is. That's 2x dx. So when we solve for dx, which we're going to need to substitute for, we get du divided by 2x. So the derivative of this always ends up in your denominator.
Mm-hmm.
So if I have something in the numerator that's going to cancel that out, then I can turn this into a perfect integral of u squared times 2x. When I substitute for dx, I put du over 2x. X's cancel out. Now I have an integral that I can integrate.
Mm-hmm.
So a lot of, I actually have encountered a few programs that don't even call this substitution. They call this using the power rule. In the same way that if I wanted to integrate sine squared of x, I could do it very easily if there was a cosine of x next to it. Because I know that the derivative of the inside, which is sine x is the inside, is going to end up in my denominator when I use substitution, and that's going to cancel out with this cosine x. So now I can just treat this as a power rule situation and go ahead and make it sine cubed of x over 3. Because I know that the derivative of the inside is going to be taken care of by that.
Mm-hmm.
Okay. Let's see here. How about the key to determining where you use substitution and where you use parts is frequently parts is used when you have two different transcendental, or you have a combination of a polynomial and a transcendental function. Something like x e to the x, here's your polynomial, here's your transcendental function, or x sine x, combination of a polynomial and a trig, or x natural log of x. These are all transcendental functions, so when you combine a polynomial with a transcendental, there's no way I'm going to be able to use substitution because, well, occasionally I might be able to with this situation here because the derivative of that is 1 over x. So but that just makes it more able to use parts. Where you use substitution is in problems like this, where you have a polynomial times a polynomial, and the inside of this polynomial, the derivative is that.
Yeah.
My book, hold on a second. Look for some other, something like this. Now, this doesn't differ much from the first problem. It's x instead of 2x, but it's not the, notice the derivative of the inside is 2x.
Yeah.
And this is only x. Well, I don't care about the 2. I can handle the 2 easily. That's a constant. I can take it outside the integral. And in fact, what they usually do in these problems, the first step is to put a 2 there and a 1/2 out here. Now I haven't changed anything. And now I have it so I can use the power rule perfectly because the derivative of the inside is exactly 2x.
Okay.
Okay? But again, that's...
Otherwise, would you use integration by parts?
Okay.
Would, if you didn't change that, would you have used integration by parts?
No. In other words, if I hadn't made it the 2x, no, I would have actually, I don't do that myself. I don't use that technique. It seems to me for an awful lot of effort for not much gain. Let's go through integration by substitution here.
Okay.
Now let's substitute. So we have x there. We have u squared. And then for dx, I'm going to put in du over 2x. Well, the x's still cancel. Now I can integrate this just fine. It's u cubed over 6.
You could also just leave it as du over 2 equals dx, right, for the substitution part? And
No.
just put that part into
Well,
the problem?
Yeah, the only reason I leave the x up here and put the 2x down there is because dx is not du over 2. dx is du over 2x. In other words, we solved for dx by going through this differentiation here.
Okay.
So we need that 2x under there. It's just that it's going to get, the x part of it's going to get canceled out by the x that was in our numerator. So this is really no different than recognizing the f of g of x, g prime of x situation. There are one other situation that I would like to apprise you of that is slightly different, and that would be this one here, where substitution unfolds a little differently. It's not always easy to see these. Well, at first glance, it doesn't look like this would lend itself to substitution, because we have an x here, and if we take the derivative of the inside, we get 2. So how are we going to get rid of this x over here? So this is definitely not a straight power rule problem. However, let's go through it. If we let u equal 2x minus 1, well now, okay, we still have to do du equals 2 dx. So dx is equal to du divided by 2 in this case. Well, now how do we rewrite our integral? Well, we could write it like this, u to the 1/2, and then dx is du over 2. But I can't integrate that because of this x. But in this situation, I can solve for x in terms of u. X is equal to u plus 1 divided by 2. So I'm just going to substitute that for x. U plus 1 divided by 2. Now I can distribute, I can multiply these two together and end up with an integral that I can handle. So this was not recognizing that composite function. This is now going to be, let's see, what do we have? Let's take these 2's outside of the integral, make everything easier, and then distribute this, so we end up with u to the 3/2 plus the integral of u to the 1/2 du. Both of them are du's. Now we can easily integrate that, and so we've solved the thing. Even though this is called a change of variable situation where you use substitution. It's different than recognizing the first case. In other words, this problem here is recognizing that the derivative of that part rests in the numerator. Not so with this problem here. The derivative of the inside part did not rest in the numerator. But we were able to define x as a function of u. So we were able to get the entire integral in terms of u. Remember, you can't integrate something unless you only have one variable and one differential. I don't know how to integrate u dv, except with parts. Only way to integrate u dv is by parts. Let's look at a parts one. Let me find one out of the book because I've already... It's amazing. In my book, there are 4 chapters in between integration by substitution and integration by parts.
Actually, same with mine too. Yeah.
Okay. And then following that, trig substitution. That's really hard.
Yeah.
But I understand it now. It took me about 2 years, but I finally understand it. I'm sure I understood it when I went to college and got a degree in math, but that's been a long time ago. So, here, let's try. Let's do one that we haven't done all the way through that requires more than one iteration. All right. Help me get started here.
Okay, so your x squared is going to be u. U is going to be x squared. Sine x dx is dv.
Okay, next step.
Du is 2x dx. And dv is negative cosine x.
So v is negative cosine x.
Yeah.
Okay.
And now
So now my master formula is this.
Yep. So it just so happens that the original equation is always of the form integral u du
That's a v.
or dv.
Yes, it is. And that's why we have to separate this entire thing. One of them has to be u, and the rest of it has to be dv.
Okay.
Okay? That's probably the hardest thing to understand about integration by parts, is how can you let dv equal this whole thing? But don't try to understand it. Just know that, figure out what to make u and make everything else dv. So now, what do we have?
We have x squared, set that equal to x squared or negative x squared cosine x minus integral to negative 2x cosine x dx.
All right, so let's see. So it's the negative. Okay, let me just write it in order here so I don't confuse myself. And then dx, hold on a second, I already confused myself. I'm writing it as v du, so this is 2x dx. Okay. Okay, and now we have to do a second iteration, because I don't know how to integrate this either.
So can you move the negative sign and the 2 outside of that integral?
Yeah.
Mm-hmm.
Okay. Now begin
So
again.
now we have to do it again.
Uh-huh.
Okay.
I guess there's no harm in using the same letters and same variables, as long as you realize you're on the second iteration.
Mm-hmm.
Whoops. So now we have minus x squared cosine x plus 2 times, let's put brackets here.
Okay.
And now
X
our
sine X.
new uv is x sine x minus the integral of sine x
dx. Okay.
dx. Okay, and this integral can be replaced with negative cosine.
X. Yep.
And then we just have to make that a plus and distribute the 2
Okay.
for a final answer. And okay, let me look and see if I can find any other interesting integration by parts problems. You haven't had to find centroids or anything?
No.
Okay, good. Because I remember doing it, but, okay, and I did get those reduction formulas right. Sine squared is 1 minus cosine 2x over 2.
Okay.
Cosine squared is 1 plus cosine 2x over 2.
Okay. You want to do a shell method volume problem?
Sure. Here, I can find that in this book also.
Okay. Is it possible to do one where we revolve around the y-axis and then x-axis,
Yeah.
or x equals 2, or y equals?
In fact, here's one that's perfect to illustrate both techniques.
Good. Meaning the shell method and the washer method?
Yes, and why the shell method is preferable.
Right.
If we have the line let's see, the function is y equals x squared plus 1, which looks like that. And it's also bounded by y equals 0, x equals 0, and x equal 1. So basically, have this area, and we're going to revolve it about the y-axis. So we'll end up with a solid that looks something like that. Notice that we can use washers. Well, we could use washers, but if you use washers, you have to do it in 2 steps. You have to do from here to here, where the inside radius is 0, and then you have to do a second step from here to here, where the inside radius is this measurement here,
Yep.
for the x value. if we do it with cylindrical shells, oh, and using the washer method, we would be integrating along the y-axis because the skinny measure of each washer is going to be parallel to the x-axis and perpendicular to the y-axis. So we would integrate along the y-axis. And notice that wherever you have a situation where you can use either washers or shells, shells always integrates on the other axis that washers does. In other words, if I'm going to use cylindrical shells here, my first shell starts in the middle. The skinny part of that shell is a dx. In other words, I've taken my dollar bill and held it horizontally and wrapped it around to create a shell. And then I would build outwards. My next shell goes from there to there. My next shell goes from there to there. And if I use shells, I'm going to integrate from 0 to this point right there. Let's see, where is that equal to? What's y equal to and x is equal to 1? That's 2. But this is 1 here. So if I integrate this with cylindrical shells, I can do it all in one step. I'm going to go from 0 to 1. Since I have a function of x, I don't need to change it because I'm differentiating along the x-axis, so I would just differentiate this. And there's my answer. Well, excuse me, hold on. We have to apply the formula for shells.
Yeah, I was worried there.
Okay, so the formula for shells, the volume of each shell is the height times 2 pi r, which is the circumference. So the height is the y measurement, x squared plus 1, and times 2 pi x, because the radius is x. So I can take the 2 pi out, but I leave the x in.
Tell me why the radius is x again. I've already been through this.
If I'm looking at each shell here, let's take this outside shell that I drew. What is its radius? It's the measurement in that direction horizontally, and that's the x point of this function.
Okay.
Okay, so that's where I get this x from.
Yep.
Okay. The other x squared plus 1 is the y portion. In other words, each one of these shells, if you unwrap that soup can label or dollar bill, this measurement here is y. This measurement here is 2 pi x.
Mm-hmm.
And y, since it's a function of x, I can describe it as x squared plus 1 times x times dx. So everything's a function of x and I'm fine. If I was going to integrate this along the y-axis, which I would do, I would actually use 2 steps. In the first one, I would use disks. In the second one, I would use washers.
Okay.
Not really any different than using washers the whole way, but with an inside radius of 0 from here to here. That's the only difference between a washer and a disk, is the inside radius is always 0 on a disk.
Can we just set up that integral?
Sure. There it is. So let's multiply the x. So I end up with 2 pi from 0 to 1 of x cubed plus x dx.
I'm sorry, I mean the washer method.
Washer integral? Okay.
Yeah. here, do we go from 0 to 2?
Well, we got to do it in two parts. So first we go from 0 to 1
Okay.
with 1 disk radius. So first of all, since we're going to integrate along the y-axis, we need our function to be a function of y. So I have to solve this for x. So x is equal to plus or minus the square root of y minus 1.
Mm-hmm.
Okay? Well, if I'm going to use disks, here, let me erase these shells. And the disks, first one is going to be like that along the bottom. So I'm going to use disks from 0 to 1.
Mm-hmm.
So the 0 to 1, the area of each disk is pi r squared. Well, r is the x measurement, which is this. And I will take just the plus side of it because that gives me the radius. There's the plus side there. That's the negative side there. So I'm going to integrate y minus 1 to the 1/2 dy plus, that gives me this part here, plus from 1 to 2, I'm going to use washers where the outside radius is 1 and the inside radius is this function. So the outside radius squared minus the inside radius squared dy. So that should give you the same exact volume between those two integrations. And this one
Do
I
you need
can
a
use,
pi in there somewhere?
yeah, excuse me. It's pi r squared, so the pi gets factored out to there, and it's pi r squared also there. So that's the problem with factoring that pi out, is I always forget about it.
Yeah. So is for that first part,
Mm-hmm. From here to here.
yeah, so the function y minus 1 to the 1/2 is
The radius,
the radius.
because that's the x measurement. Remember that x is equal to y minus 1 to the 1/2.
So is that like saying that is that like saying that that vertical line at x equals 1?
Well,
that,
yeah, let me rethink this a little bit. It's really just 1, isn't it? I don't need this function because it's not a variable in this part. It's just 1. Does that look better?
yeah.
Yeah,
Okay.
that's more correct. Yeah.
Now, what if you?
Yeah, it's after we get into this part, the radius becomes x.
Yeah.
Yeah, the radius isn't x down here. Excuse me. Yeah. Yeah, the radius down here is always 1. Okay.
Now, if you revolved that area around the line, like y equals 4, you would use probably the shell method for that.
Did you
Or, I'm sorry,
revolve it around a vertical line?
horizontal line.
Okay, so y equals,
I think you would
say,
need more room to draw it.
yeah, let's do y equal 3.
Okay. Yeah.
Okay. So we're going to take this shape and revolve it around that line.
Yeah.
Now, first of all, there'll be some empty space here.
Right.
There'll be a giant hole, which is okay. Let me think about this for a moment. So is all we have to do is after we revolved it around that line, we're going to use washers that are perpendicular to which axis?
The y-axis, or sorry, the x-axis.
Right, the x-axis. Okay, so we don't need to picture this. I mean, we don't need to draw it. We can tell what the outside radius is going to be and what the inside radius is going to be. So I'm going to integrate from 0 to 1. What's the outside radius squared? We need a pi here.
The outside radius would be 0.
3.
Right?
Be the distance from here to here.
Okay.
So that would be 3. The inside radius is this distance from here to here throughout. So I can do this whole thing in one step. So I got to subtract, let's see, the outside radius squared minus the inside radius. Well, what is that? That is 3 minus y. In other words, if this is y, the distance from here to there is 3 minus y.
Right.
So I'm going to subtract 3 minus y, and y is x squared plus 1. So that quantity needs to be squared, dx.
Okay.
And that's easy enough to do. In other words, you can simplify that by combining the 3 and the negative 1. And you can actually perform the square, subtract that, and you'll end up with a polynomial of 4th degree, which can then be separated into a bunch of integrals and integrated using the power rule.
Would it be just as easy to use the shell method here?
Well, not really, because if you rotate this about the line y equal 3, I'm trying to picture that, how you would, I guess you could make that with shells, or could I? I'm trying to figure out what that thing's going to look like and whether I could use shells. I guess you could, because the first shell would have a hole in it that would be 2 units wide.
Yeah.
So you could use shells that are, the dollar bills are laying on their sides, and the skinny part of the shell would be a dy. Yeah. You could use shells, I guess.
Mm-hmm.
The height of each shell, well, this outside shell is going to have that height and this radius. And the inside shell is going to have this height and this radius. All right. Any other last general questions that you might want answered? That's a horrible question for calculus, but
Yeah. I think that's actually
because
pretty much
everything is a specific question.
yeah. Thank you very much.
You're welcome, and hopefully it'll help you for your test. Your test is today, right?
Yep, it's at 11.
Well, I got a lot more fun things to do than take a test. I'm going out and playing golf.
I'm going to Red Rocks tonight.
Ah, okay.
Good.
Yeah, out trump me.
Yeah.
Who's playing? Who are you seeing?
I'm seeing some like crazy electronic.
Oh, all right. Well,
Should be fun.
yeah, Red Rocks is an experience in itself, regardless of who's playing.
I guess there was a huge concert last night too.
Uh-huh.
So
Yeah.
a bunch of my friends went,
Yeah.
including my math TA. went.
Oh, really?
Yeah. So that was funny.
Yeah.
Yeah.
All right, Dominic.
Well, have a good day.
You too?
Don't lose any balls in the water.
Yeah, that'll be a first. All right.
Okay.
I'll talk to you later.
Thank you.